Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and good afternoon. So today our group will explain about heat exchanger co-current flow. So before that, we will introduce ourselves first. So next. So my name is Nurul Izzah binti Azmi. My metric number is 197083.
My name is Sofea Hani binti Tazam and my metric number is 198689.
My name is Nurazliyani binti Jamaluddin. My matrix number is 198681.
My name is Nuraina binti Ruzi. My metric number is 199141.
Okay, so I will explain about the co-current flow. So for the co-current flow in the heat transfer fluid, the heat transfer fluid will be a coolant for exothermic reaction and a heating medium for endothermic reaction. So if the flow rate of the heat transfer is sufficiently high with the respect to the heat transfer or absorbed by the reactive mixture, then the heat transfer fluid temperature will be virtually constant along the reactor. So in the material that follows, and next slide. So in the method that follows, later we will develop the basic equation for a coolant to remove heat from exothermic reaction. And same equation also will apply to endothermic reaction where a heating medium is used to supply heat. So next. So later, Aina will explain about how to carry out an energy balance on the coolant in the analysis between R1 and R2 and between volume and volume plus difference of the volume as shown is in the figure. So the mass flow of the heat exchange fluid is Q. And in this energy balance, it will consider the case when the reactor is cooled and the outer radius of the coolant channel R2 is insulated. And remember that convection is the heat added to the system. So next, I will pass to Aina.
Okay, thank you, Izzah. Assalamualaikum. So, I'm going to explain about the energy balance or the coolant in the volume between V and V plus difference of V. The rate of energy in at V minus rate of energy out at V plus difference V plus rate of heat added by conduction through the inner wall equal to 0. Okay. By dividing the change of V and taking limit as 0, it will become this formula, and the change in enthalpy of the coolant, as in the book said, become the Cp dTA per dV. By the way, about the TA is the temperature of the heat transfer, which is coolant, and T is the temperature of the reactive mixture, which is the inner tube. And lastly, it will become the variation of the coolant temperature, TA down the length of reactor, which is UA, multiply T minus TA per MCCP. Okay, next. Okay, typical heat transfer fluid temperature profiles are shown for both exothermic and endothermic reaction when the heat transfer fluid enters at T and node. Wait, where is the annotate? Okay. Okay. As we see at this, as we did at this, the exothermic, TA node is the inlet and TA is the outlet. So A is for the coolant. So when the TA node enters at the low temperature, and the outlet will become a high temperature, while in the heating medium for the B, the TA node will enter at high temperature and the outlet will become at low temperature. Okay, next I will pass to Sofea.
Okay, thank you. Thank you, Aina. Okay, Assalamualaikum. Okay, so I will explain about algorithm for PFR and BPR design for gas phase reaction with heat effect. So there are two cases. So the first case is case A, which is the conversion as the reaction variable. Okay, so for examples, there a reversible reactions, which is A plus B equals to 2C. Okay, first step is you need to find the mole balance for this reaction. So this is the formula for the mole balance in PFR and PPR. And then we need to find the rate law, and we assume that this reaction is elementary reaction, and we will use this formula to get the K, the value of the K constant. And then for a condition for Cp equals to 0, we can use this formula, which is Kc. Okay, next step is we have to find the stoichiometry for the reaction. Since the gas phase, so it means that there is no change in P in this reaction. So this is the stoichiometry to find the concentration for all mole component Ca, Cb, and Cc. And then the last step is to find the energy balance, which is in reactor. We are using this formula dt dv. And then for current coolant, we are using this dT8 over dV, as what I already explained earlier. And next, I will pass to Yani for the second case.
So hi, okay, so for case B, it is a mole of flow rate as a reaction variable. So what we need to do is first we have to do the mole balance. Okay, remember the previous case, this is algorithm for PFR and PBR. So this is the design equation for PFR. So we do for each component RA, RB, and RC. So the second step is we find the rate law. Okay, remember this is in this example we use elementary reaction, and we get negative RA is equal to K1 CACB minus CC square over KC, and we find K, which is equal to this equation, and KC the equation is KC2 multiplied with T2 exponent delta heat of reaction over gas constant multiplied with 1 over T2 minus 1 over T. The next step is stoichiometry, which is in PFR is gas phase with no pressure difference. So we can find the RB, RC, CA, CB, CC, and the total flow rate, which is equal to FA plus FB plus FC. And then we do the energy balance. For this reactor, it is dT, differential of temperature over the volume, is equal to UA multiplied with temperature of the coolant minus T plus negative RA minus and multiply with the heat of reaction over FA CPA plus FB CPB and FC CPC that we calculate earlier. So in this heat exchanger, if the heat transfer fluid, which is coolant temperature, TA is not constant, the energy balance on the heat exchange fluid give this formula, which is a differential of TA over dV is equal to UA T minus TA over MC CPC, which is this MC is the mass flow rate of the coolant in kg per second, and CPC is the heat capacity of the coolant in kg over kgk. So for the parameters evaluation, we input all the parameters here into the equation. So for case A, the conversion as the independent variable, which is K1, E, R, CTO, TA, T0, T1, T2, KC2, and W, heat of reaction, CPA, CPB, CPC, and UA, we insert it in the equation with initial values of T naught and X equal to 0 at volume is equal to 0, and we can find the final values of the volume. So for the case B, for molar flow rates as independent variables, it is the same as case A, except that the inlet values of FA naught and FV naught are specified instead of X at V naught. So that's all from us. Thank you.